Hello, everyone. My name is Nina. I am from Ghent University in Belgium, and I will present our paper together with Maxim, Lingchen, and our professor Aleksandra. Our paper is on deep image hashing based on twin bottleneck hashing with variational autoencoders. So before I talk about our image hashing method, I first want to motivate why one would even want to do image hashing. So say you have an image, for example, of a city landscape, and you are interested in knowing which city is pictured in this image. Well, one way of finding that out is by using Google image search, where we can upload an image and Google retrieves the visually and semantically similar images, as well as some information about those images from these corresponding websites. So this is content-based image retrieval. Now, the way content-based image retrieval works is as follows. So we take a query image. Using a hash function, we calculate a hash code for this image. And then we look up similar hash codes in the database and retrieve images corresponding to those hash codes. Just to note, the term image hashing shouldn't be confused with hashing in cryptography terminology, because in image hashing, we want a small change in an image to actually result in a small change in the hash code. So there are different approaches to designing this hash function. Traditionally, this would be done using handcrafted techniques, so not relying on any data. However, in recent years, with the progress of deep learning, achieving good results in other image processing tasks, people have started using it also for image hashing. And there we have supervised and unsupervised techniques. And for us, unsupervised techniques were more interesting to perform research on, because for the supervised methods, we would need to have large labeled data sets. So some of the most common unsupervised neural networks for deep image hashing are autoencoders, adversarial networks, and graph-based networks. So now I will introduce an unsupervised deep hashing method from CVPR last year, on which our method is based, and which we improve. So it is relatively complex, so I will be building it step by step. Starting with the autoencoder structure, so we have this bottleneck, which will be our hash codes. Of course, we want the bottleneck to be very constrained, for example, 32 bits. But this comes at the cost of the model being very restricted. So for this reason, the hash representations suffer. So the authors of this paper would added a continuous bottleneck, which is much larger, and it would share the encoder to generate better codes. And these two bottlenecks get aggregated through a graph convolutional neural network. I won't go too much into detail here because we don't change this part. And the last thing to note is that there is some regularization applied here. So we'll just focus on the discriminator for the binary bottleneck, so it tries to distinguish between actual random codes and the generated hash codes. And the idea is that this would help with the disentanglement of the latent variables, which are actually the bits of the hash code. So this is a very recent method from last year from CVPR. And now I will talk about how we improve this method. So for the first improvement, we looked at how the binary codes are generated. So we realized that if the hash code bits or the latent variables, if they would be disentangled, the distances between, or more disentangled, the distances between codes would become more meaningful, and that would translate into having better hash codes and therefore also better image retrieval results. So by disentanglement, just a note, I mean, for example, how in beta variational autoencoders trained on images of faces, we have latent variables, one latent variable for gender, for example, one for skin color, etc. So we replace this bottleneck with a recent method that is similar to beta variational autoencoders. And furthermore, we could also discard the discriminator, which was used to keep the variables independent, because now this was already done by this variational autoencoder. And removing this discriminator also saved us some computational cost and also made the model simpler. And this indeed improved our model, as we will show in the results slide later. So this was the first improvement. Now, as for our second improvement, it was on the continuous bottleneck. So the idea is the continuous bottleneck is responsible for the good representations. But this was originally a classical autoencoder bottleneck, and we replaced it with something that should allow the model to better capture the input data, specifically boosting the shared encoder, and therefore also achieving better results when generating hash codes. So we used a robust algorithm for optimizing variational autoencoders called GECO, which stands for Generalized Elbow with Constrained Optimization. And this allowed us to better control the trade-off between compression and the reconstruction quality of the generated samples. So here we present the evaluation in terms of the precision recall curves on the CFAR10 dataset. We show the baseline twin bottleneck hashing model in orange, and it has been outperformed by each of our improvements separately. So here shown as dashed blue lines, and both of them together show an even larger improvement, so shown as a solid blue line. And this is the case for all the hash code sizes, so 16, 32, and 40, and 64-bit. And we also see an improvement on an even larger data set with more object classes. So the MS COCO data set, again, on all hash code sizes. So here we evaluated our method in terms of mean average precision. And we show results in the table. And we included mean average precision of all the state-of-the-art unsupervised deep hashing methods. And we see that our method performs the best. And on the right, we show some retrieval examples for both our method and in the top row, and the TBH method in the bottom row. And the correctly retrieved images are labeled in green. So to summarize, we improved the binary bottleneck of twin bottleneck hashing by using a variational autoencoder with disentangled variables and by omitting the regularizer. We also improved the continuous bottleneck of the twin bottleneck hashing to use a variational autoencoder with a constrained optimization setup in order to better control the trade-off between compression and reconstruction quality of generated samples. Both of these showed improvement separately and an even larger improvement together. And we, in this way, outperformed the state-of-the-art unsupervised deep hashing methods on different data sets and for all hash code sizes. So you can find our paper and these slides if you scan the QR code. And I want to thank you for your attention.